This section introduces MATLAB, Simulink, and Simscape as one idea seen from three heights. Three tools, one dynamic system, viewed at three levels of abstraction. That is the whole chapter, and the rest of the book computes in the vocabulary it hands you. MATLAB is the ground floor. You type the mathematics directly, functions, matrices, derivatives, plots, and it returns numbers. Simulink lists that to a wiring diagram whose blocks are themselves the mathematical operators. You draw the equation as signal flow instead of writing it. Simscape lifts once more. Its blocks are physical components, a mass, a resistor, and the equations are inferred from how you connect them. The move that does the real work is that last jump. You stop encoding the equation and start encoding the object, letting topology recover the math. This section explains one dynamic system seen through three names, where the only difference is what each treats as primitive. MATLAB takes numbers and functions. You compute values imperatively, writing something like the square root of the sine of 3 pi over 4, and you package reusable steps as scripts and user functions. Simulink takes the signal. It is a directed graph of operators wired to root time, varying quantities, so computation is flow rather than statement. Simscape takes the physical port. Its components form undirected networks, where a wire means a shared across and through variable, and energy is conserved rather than a data path being carried. That split between across and through variables versus signals is the real boundary. The chapter's job in the book's arc is to install all three lenses first, so that every later system can be posed in whichever representation makes its constraints fall out as identities. This section explains why a whole chapter on complex analysis, differential equations, and the Laplace transform hangs together as one idea. Differentiation is the expensive operator, and the whole chapter exists to make it cheap. A linear ordinary differential equation with constant coefficients resists direct attack because the derivative operator, d by dt, couples a function to its own slopes. The Laplace transform conjugates that difficulty away. It carries the time function x of t into the transform function capital X of s, and under the map, differentiation becomes multiplication by s and integration becomes division. The differential equation collapses into an algebraic one. You solve it by ordinary algebra in the S domain, then invert back to time. Complex numbers precede. All of this because S is complex, and the transform's whole geometry lives in that plane. The structure is identical to the logarithm, turning products into sums. Find the domain where your hard operation is, someone else's easy one, work there, and return. This section explains the single move that underwrites the whole chapter. When an operation is painful in its native domain, find an invertible map to a domain where it turns trivial, act there, and map back. Differentiation is the feared operator. The Laplace transform sends d by dt into multiplication by s, so a differential equation collapses into ordinary algebra in the S domain. You solve it there, then invert to recover the time solution. Complex numbers are the same trick one floor down. They give you the plane where rotation becomes multiplication and a system's natural frequencies become mere points. The three main tools are one move, conjugate by a transform until the operator you fear becomes arithmetic. Everything later in the book computes in the frame this chapter buys. This section explains what a matrix is and why matrix analysis anchors a dynamic systems book. A matrix is what coupling looks like once you stop writing the equations one at a time. Several unknowns tangled across several equations become one object, call it A, and every question about the tangle reduces to a scalar you read off that object. Solvability, redundancy, and invertibility collapse into rank, determinant, and invertibility. Collapse into rank, determinant, and inverse. The chapter's real move, and its reason for existing in a dynamic systems book, is the eigenvalue problem. The same invariants that resolve a static coupled system carry over to differential ones, where the eigenvalues become natural frequencies and the eigenvectors decouple the motion. Algebra first, and then the identical structure governs dynamics. This part explains why matrix analysis is really the study of coupling. And where the chapter is heading, coupling is the whole subject. The matrix is its algebra. When several unknowns tangle across several equations, no equation is solvable alone. The tangle itself is the object of study. A matrix collapses that web of scalar relations into a single operator. One thing you can transpose, invert, and multiply as a unit. The chapter's real destination is the eigenvalue problem. Find the frame in which the operator acts by mere scaling. In that frame, the coupling dissolves, the natural frequencies fall out, and a coupled system of differential equations splits into independent ones. So matrix analysis is the move that makes a dynamic system's internal entanglement addressable, not arithmetic on arrays. Everything the book later builds, state-space dynamics, is composition in this language. This section explains why a linear dynamic system has one behavior wearing 5 faces, all of them interconvertible. One system, 5 faces, all interconvertible. That is the whole chapter. A linear dynamic system has an invariant behavior. The configuration form, the state space, the input-output equation, the transfer function, and the block diagram are 5 coordinate charts on one and the same object. The spine of the chapter is the claim that any one of them yields any object. The generalized coordinates qi are chosen, not given. The choice is free, the count is fixed, so representation is gauge and dynamics is content. The second-order matrix form is the mechanical anchor, m times x double dot plus c times x dot plus k times x equals f. Everything downstream, the derivation in chapters 5 through 7, and the solution in chapter 8, presumes you can slide between faces at will. Linearization is the toll for admitting a nonlinear system to this club. This section explains the 5 representations of a single linear system and why they are all the same object. One linear system has 5 faces, and every face is the same object seen from a different operation. Configuration form carries the raw equations of motion. State space rewrites them as first-order flow, ready for a machine to integrate. The input-output equation and the transfer function discard the integrate. The input-output equation and the transfer function discard the interior and draws the wiring. The chapter's whole claim is interconvertibility. Any form derives from any other, so a representation is a choice of coordinates on an invariant system, never new content. So pick the face that trivializes your task. Simulation wants state space. Frequency analysis wants the transfer function. Linearization is the admission fee. Bend a nonlinear system into this family first. This section explains how every mechanical system reduces to 3 basic elements. Every mechanical system collapses to 3 idealized elements, and the partition rests on a single question. To which time derivative of position is the element's force proportional? The 0th derivative, displacement, gives the spring which stores potential energy. The first derivative, velocity, gives the damper, which dissipates it. The second derivative, acceleration, gives the mass, which stores kinetic energy. That single axis generates the whole taxonomy. The energy verbs store, dissipate, and store again are the same three cases read the other way. Modeling is then bookkeeping. You interconnect the elements, impose one balance law, either Newton's second law summing forces or the energy method summing works, and the equations of motion fall out. Rotational systems are not something new. Swap force for torque, mass for inertia, and displacement for angle, and the identical triple returns. This section explains why a mechanical system collapses to exactly three idealized elements and why that three-way split is forced rather than chosen. A mechanical system reduces to exactly three idealized elements, and the trichotomy is forced. An element's force can be proportional to displacement, to velocity, or to acceleration. Those are the zeroth, first, and second time derivatives of position, with nothing between. The three elements are the spring, the damper, and the mass. The spring stores potential energy, the damper dissipates it, and the mass stores kinetic energy. That exhausts the ontology. Modeling is then mechanical. Classify each real part into one of the three. Wire them together by their shared motion and impose one conservation law, either Newton's force and moment balance or the energy method, to fall out the equations of motion. The chapter's work is showing that both laws yield the same differential model, so the choice between them is convenience, not physics. This section explains how an entire electrical system reduces to one repeated move. Every electrical element is a single constitutive law-binding voltage to current. The resistor is algebraic. Voltage equals resistance times current. The inductor and the capacitor are differential. Voltage equals inductance times the rate of change equals inductance times the rate of change of current, and current equals capacitance times the rate of change of voltage. A circuit is nothing but those laws stitched together by two conservation statements. Kirchhoff's current law says the charge flowing into a node equals the charge flowing out. His voltage law says the potential drops close to zero around any loop. That is the whole generative move. Pick the primitives, write each one's effort versus flow relation. Then glue them together with conservation. The chapter's quiet payoff is that this is the same pattern the mechanical chapters ran. Impedance makes it explicit, collapsing resistance, inductance, and capacitance into one generalized resistance. So an op-amp, a motor, and a spring all model by the identical recipe. This section shows that every physical domain wears the same skeleton, and this chapter only relabels the mechanical one from Chapter 5. Electrical elements sort into three roles: source, store, dissipate. These are the springs, masses, and dampers seen sideways. Two bookkeeping laws do all the work. Kirchhoff's current law is flow conserved at a node. His voltage law is effort balanced around a loop, the electrical face of Newton's balance. Wire the elements together and the circuit collapses to the same differential equations. The motor is the tell. It is two copies of the skeleton, electrical and mechanical, coupled through one energy conversion term. Impedance is the reward. It makes the correspondence explicit. Voltage matching force, current matching velocity, so a circuit is a spring mass under a change of name. This section explains how every fluid and thermal system in the chapter reduces to one borrowed skeleton, the RC circuit. A storage element, whether pneumatic, liquid level, or thermal, carries a capacitance, the ratio of accumulated stuff to the potential it raises. That store is fed through a dissipative resistance, the slope of a flow versus potential it raises. Close the loop with the conservation law. Mass for fluids and energy for thermal, and the same first-order equation falls out every time. Capacitance times the rate of change of potential equals the difference in potential divided by resistance. The correspondences are fixed. Pressure and temperature play the part of voltage. Volume flow and heat flow play the part of current. Stored mass and stored energy play the part of charge. The chapter's whole move is that translation. Model the unfamiliar domain by mapping it onto the circuit you already solve, then let Simscape integrate it. This section explains why every fluid tank and heated body is secretly an RC circuit. Name the two roles and the model writes itself. Capacitance is how much stuff you store per unit of driving potential, gas mass, liquid volume, or heat stored per unit of pressure, level, or temperature. Resistance is how much that potential must differ to push a unit of flow through a valve and orifice. Then a single conservation law closes the loop. Mass for fluids, energy for thermal. The rate of the stored quantity equals flow in minus flow out, which is exactly capacitance times the rate of change of potential equals the driving difference divided by resistance. That is a first-order lag. Pneumatic, liquid level, heat transfer. 3 substrates, 1 equation. The chapter's real content is the dictionary mapping each physical system onto voltage and current. The circuit is already solved. This section explains how a system's total response to an input decomposes. A system's total response to a forcing, f of t, is one function, x of t. The chapter's whole move is that this single response decomposes and along 3 independent axes at once. Split it by where each term comes from. The natural response, which is the homogeneous free behavior, plus the forced response, the response to the input alone. Split it by asymptotic fate, the transient, everything decaying to zero, plus the steady state, what survives. Split it by cause, the zero input response, the response to initial conditions alone, plus the zero state response, the response to the input alone. Same x of t, 3 orthogonal factorizations, each isolating a different question you might ask of it. Master the axes and every worked example, first order, step, impulse, nonlinear via the fourth order. Runge-Kutta method is just this superposition, read from one chosen angle. This section explains how linearity lets one response be sliced 3 ways. Linearity buys you one thing, and this chapter spends it 3 ways. The total response of a linear system is a sum, so you may slice it along whichever axis the input alone. By origin, natural or homogeneous, plus forced. By asymptotic fate, transient, the terms that die as t goes to infinity, plus steady state, what's stead as t goes to infinity, plus steady state, what's zero input, the initial condition alone, plus zero state, the input alone. These are 3 partitions of one quantity, each term computed in isolation and re-added. Superposition is the only machinery. Predict the next case from this. Kill the input and only the natural or zero input slice remains. Wait long enough and only steady state does. Every type of response is a projection, not a new phenomenon. This section introduces vibrations. A restoring force pulls a displaced system back toward equilibrium, and inertia carries it past. That loop is oscillation. That single feedback is the entire subject, and it is nothing new. It is the same second-order equation the earlier mechanical and response chapters already built. M times x double dot plus b times x dot plus k times x equals f. Here it is read through one lens, what oscillates and how fast it decays. One dial, the damping ratio zeta, sets the regime harmonic oscillatory decay or aperiodic. And one distinction, whether the drive is an initial kick or a sustained external force, splits free from forced. Everything downstream, the isolators, the absorbers, the modal decomposition, is a variation on that equation, never a departure from it. This section explains how a restoring force turns motion into vibration, and how a single number sorts every possible response. A restoring force turns dynamics into vibration. Displace the system, and elasticity or gravity pulls it back. It overshoots, it oscillates. The whole chapter is one equation specialized, the second-order linear ordinary differential equation, mass times the second derivative of position, plus b times the theta is between 0 and 1, and undamped when zeta equals 0. Everything downstream is a single scalar, the damping ratio 0. Everything downstream is a single scalar, the damping ratio zeta, and that one zeta is greater than 1. Critically damped when zeta equals 1. Underdamped when zeta is between 0 and 1. And undamped when zeta equals 3 verbs follow. Learn to read zeta off a decaying trace through the logarithmic decrement. Learn to reduce its effect with isolators and absorbers. And learn to generalize it to many masses, where the eigenvalues become the natural modes. Free versus forced is just which term is non-zero, an initial condition or a driving force. Predict the next system by finding its zeta, and the taxonomy follows. This section introduces feedback control, the layer where a controller is defined by the discrepancy it nullifies. Feedback control closes a loop. It measures the output, subtracts that from the reference, and drives the plant by that error alone, never by the target directly. The cruise control anchor carries the idea whole. The throttle responds to the gap between 60 and the speedometer's reading, not to the figure of 60 kilometers per hour itself. So the loop hunts its own fixed point and holds there against hills and headwind. 4 organs suffice: plant, controller, actuator, sensor. That is exactly the minimal cycle that lets a system sense its own output. Now the boundary. Cut the sensor line and error becomes fiction. You are back to open loop, steering blind, trusting the model instead of the world. This section explains what feedback is and why closing the loop turns an error into a driving force. The gap between where a system is and where you want it to be is not a readout. It is what drives the system there. Close the loop, and the error, E equals R minus Y, becomes the actuating signal. The plant chases its own reference, and it silently corrects whatever the model failed to predict. 4 parts compose the loop: a plant to control, a sensor to measure, a controller to compute, and an actuator to drive, wired so that output re-enters as input. Subtract the feedback, and it stabilizes. Add it, and it diverges. One structure carries 2 intents, named only by the reference. Hold constant against disturbance, and you have a regulator. Follow a moving target, and you have a servo.